Hello friends and welcome to this video in which we will learn about asymptotic notations in detail. So let's get started. The first asymptotic notation is the big O notation. The big O notation defines an upper bound of an algorithm, which means that time cannot grow faster than this. It indicates the maximum time required by an algorithm for input values. It represents the worst case of an algorithm time complexity. While analyzing an algorithm, we mostly consider big O notation because it will give us an upper limit of the execution time, that is, the execution time in the worst case. Let us now look at the formal explanation. If we have a function gn, then big O of gn is defined as set of all the functions fn for which there exists some constants c and n naught such that fn is less than equal to c times gn for all n greater than equal to n naught. Let us take an example and understand it more clearly. Let's say that we have a function fn equal to 2n square plus 3n plus 1 and gn equal to n square. If we use c as 2 plus 3 plus 1, that is 6, then fn will be less than 6n square for all n greater than equal to 1. So, for c equal to 6 and n naught equal to 1, we can say that fn is an element of the set big O of n square. Let us now plot these two functions on a graph. This is our fn and this will be our c times gn. And this is the n naught, which is equal to 1. You can see that after n naught equal to 1, c times gn is always greater than fn. That means fn never grows at a rate faster than c times gn after n naught. Note that c and n naught can be chosen differently and still you may get the condition satisfied. Let us now look at the next notation. The next is the omega notation. The omega notation defines lower bound of an algorithm, which means that time cannot grow faster than this. It indicates the minimum time required by an algorithm for input values. It represents the best case of an algorithm's time complexity. While analyzing an algorithm, we rarely use the omega notation. Let us now look at the formal explanation. If we have a function gn, then omega of gn is defined as set of all the functions fn for which there exists some constants c and n naught such that c times gn is less than equal to fn for all n greater than equal to n naught. Let's take an example and understand it more clearly. So we have this function fn equal to 2n square plus 3n plus 1 and gn equal to n square. For all n greater than equal to 0, this 3n plus 1 will be greater than equal to 1. So if we have c equal to 2 and n naught equal to 0, then clearly 2n square will be less than equal to fn for all n greater than equal to 0. Hence, we can say that fn is omega of n square. Let us now plot these two functions on a graph. this is our Fn, and this will be our C times Gn. Let's also mark n naught equal to 0. So we can clearly see that C times Gn never exceeds Fn for all n greater than equal to n naught. The next is the theta notation. The theta notation bounds a function from above and below. It consists of all the functions that lie in both big O and omega expression. It represents the average case of an algorithm's time complexity. If we have a function Gn, then theta of Gn is defined as set of all the functions Fn for which there exists some constants C1, C2 and n naught such that C1 times Gn is less than equal to Fn is less than equal to C2 times Gn for all n greater than equal to n naught. Let's take the same example again. So we have this function Fn equal to 2n square plus 3n plus 1 and Gn equal to n square. So we can choose C1 equal to 2, C2 equal to 6 and n naught equal to 1, then our inequality will hold. Hence, we can say that Fn is theta of n square. Let us now plot the graph. This is our Fn. This will be C1 times Gn and this is C2 times Gn. And this will be our n naught, which is equal to 1. So we can see that Fn is bound by these two functions C1 times Gn and C2 times Gn. In the next video, we will take some examples and try to reduce the time complexity of some algorithms. That's all for this video. Thank you for watching.